that's when we talked about the physical layer, the data link layer, network layer, etc. So if you do, sometimes in this class, I get people that's already taken the Security Plus. So there is the option to take the Network Plus if that's what you want. I just need to be let known prior. Um, as a matter of fact, Una, can you send an email to the people from the last cohort and let them know that they need to tell me what type of what voucher they wanted?
Okay.
All right. Did you already fill out the paperwork for it and turn it into Rochelle? Okay, so just ask the students what type of voucher they want, and then when it says eligible for voucher or whatever, maybe we can indicate which one they want right there. Okay, so the default voucher for this class is the Security Plus, but if you decide you like networking, sounds good. But we are only going to spend about a week on networking, so that will require a little extra self-study. But we will go through a lot of networking. Okay, so share the screen. All right, so explaining the OSI and TCP/IP models. So we're going to talk about explaining the OSI models layers and explaining the TCP/IP suite. So this is going to cover specific exam objectives. So just like the Security Plus had a ton of exam objectives, this does too. And so this is going to cover parts 1.2, which is explaining devices, applications, protocols, and services at their appropriate layers. So a lot of the questions you'll get, it'll be like, this device operates at, it might tell you what the device is. So a router operates at what, at this layer 2, I mean, not layer 2, but at this level of the OSI model or something like that. And then you need to know that, a router is operating at layer 3. And then it's talking about explaining the concepts of characteristics of routing and switching. So switching is kind of moving things within our network according to their MAC number, and we'll get into what a MAC number is a little bit further on, and routing is going to do it by IP number. So network boundaries. So a network is going to be 2 or more computer systems that are going to be linked together by some sort of media to share information. So media meaning wires, media meaning radio frequency waves. That's what Wi-Fi is running off of, right? And so it doesn't matter whether the network has 2 or thousands of machines. It's just the concept is going to be the same. We're going to have nodes and we're going to have links. So the nodes are going to be devices that communicate on the network, and the links are going to be the communication pathways between each one of these nodes. So a network is going to provide its services to the users, and these services are going to be things like shared files, shared folders, printers, email, databases, etc. And then that was, back in the day. I mean, we still do that stuff now, but now we have even more services because we have web applications, we have voice over IP. Fun fact: most of our conversations on telephones are carried over the internet as well. Even if you're not necessarily like on Wi-Fi, it still travels a lot of the length through the internet using the VoIP protocol. And then we have multimedia conferencing, which is what we're doing right now. So we have all different types and sizes of networks, and so a single network location, like what you're on right now in your house, all the devices in your house, they're on a LAN. So you have your main router, and that's going out to the internet, but you also have all your devices in your house that are connected to that router. So that is your local area network. And then once it leaves your house, right, it goes into the wide area network, which is pretty much the internet at large. All right, so the OSI model. So we have the application, the presentation, session, transport, network, data link layers. And we're going to go a little bit further into all of these, but we got, so the physical layer, just a mnemonic to remember, because usually what I do if I go take one of these tests, I'll go write it down second I get in there. So for this, it'll be something like, please do not throw sausage pizza away in order to remember it. Or it could be, all people seem to need data processing. Oh, sorry. All people seem to need data processing. So either one, whatever one can help you remember it, is a good way. So the OSI model itself, we're basically trying to divide any problems or any network devices into subtasks, and having this layered approach can help people kind of like figure out how to debug or how to design what they're doing for their internet connection. So not, as I told you guys Friday, not everything fits neatly in here. But it's not a standard, it's not a specification, it's just a guideline for designing network protocols and stuff. So protocol data units. These are rules for exchanging data so that they can communicate in a structured format. So we're gonna have two or more, we're gonna have important functions here of a protocol that's gonna be able to address, and addressing is gonna be describing where data should go. And then we're gonna have encapsulation, which is describing how the data should be packaged for the transmission. So as we see down here, so basically the process for encapsulation is gonna be, is for a protocol that's gonna add a header to whatever data it's using. So we'll have stuff like this is the data, and then these are the headers on each one of them. So this is something from the application. And this kind of tells it how it's gonna, it's directions, right? So the network is gonna use different types of protocols. And so maybe, for example, like local addressing and network addressing for switching and routing between networks is going to be performed by different protocols. So we're going to have different headers on that, right? So maybe one of these is going to say, okay, where is it located within our local area network according to like MAC addresses and stuff. And a MAC address is something that each internet device, enabled device, has a unique worldwide. It's supposed to be unique anyway, worldwide to that device. There shouldn't be another device in the world with that same number. And so one of these protocols might go for that, right? And one of these headers. And then the next one might be for the IP address. Well, the IP address is just getting it, to your house or wherever the router seems to be. And then the MAC address number, that once it's gotten in your house, then it's going to figure out where it goes from there, from the MAC address. Yeah. So the payload is the data, and the header is kind of like the instructions for the protocol, basically. All right. And so let me point this out as well. So in this case, they are encapsulating it when it's going down from, like, it starts here at the application layer and works its way down and gets new headers added on, but then it reverses that when it gets to the computer that it's supposed to go to. So we have encapsulation and decapsulation here. All right, so node, station, and host. So in layer one of this OSI layer, the physical layer, a node is going to be any device that can communicate on the network with one or more network interfaces. So a network interface is kind of what's getting us on the internet, right? You have a network interface card in your computer that's allowing you to get on the internet, right? So the term can also be used to kind of describe endpoint devices such as any computer, any laptop, any server, smartphone, whatever. It's going to be the node, right? So all of us are basically nodes on a network. So the node on a wireless network can also be called a station. And then the host, a host is used means the end system device, such as what we're using right now. We're on a host, and we're hosting what, all these VMs and stuff like that. And then so transmission media. So the link between network nodes is going to be created using some sorts of transmission or physical media. So this will be, like I said before, a cable. However, wireless is going to use radio transmissions. And then the physical layer of the OSI model is going to be responsible for the transmission and the receipt of all the bits from one node to another. So at that physical layer, there's something called a segment, and this is where all the nodes share access to the same media, meaning wire, etc. And then the network is divided into segments in order to deal with whatever physical restrictions that network media use, such as performance or something like that. So we have several different devices. Well, physical topology. So when we talk about physical topology, that's going to be the layout of all the nodes, right? And we'll like kind of draw that out or something like that. We can have a physical interface, and so that's going to be mechanical specifications for a network, such as like cable specifications, the media connectors, pinouts. So there's various pins inside these wires that they're special. They have to be correctly linked up and everything. So there's devices that are operating on the physical layer, and so we have. Oh, I wonder if it's gonna be on the next one. Yeah. So the devices that we'll see here are going to be like transceivers. So transceivers are a network interface that's going to send and receive signals over that media. Then we have media converters. So this is a device that's going to convert one media signaling type to another. So maybe move us from Wi-Fi to Ethernet, right? Or maybe from cable, like coax cable, to fiber optics, right? We have hubs and repeaters. So a repeater is a device that's going to amplify the electronic signal to extend the maximum allowable distance of that media. So that way, when we are sending something across the network, let's think of it like telephone lines. Well, let's say the thing is, when we're traveling stuff over these wires on the internet, the signal kind of degrades after a while and gets slower and stuff like that. So let's say the power pole lines, let's say in between each one of those power pole lines, for instance, right? This is not really what's happening well, maybe they are actually on there. But anyway, you'll send something through the power pole line, right? Let's just say our Ethernet cables are up there. And then we're going to have a repeater at each one of those poles. So that way the media, the system is boosted again, right? And so we'll have a repeater every so often to extend that maximum distance. And then we have something called a hub. And that is a multi-port repeater. And this is going to be deployed like at a central location, but they're not even really used anymore. So you just need to know that hubs repeat whatever signal goes into them. What happened? No. What is this? All right. So next up, we have the data link layer. So that's layer 2. Most networks are not like directly connecting their hosts together. So they're basically making a host establish a link with one another, and then each host is going to be connected to a central node, like a hub or a switch or a wireless access point. So basically, all your cell phones at your house, all your computers, those are all nodes in your network, and then that central place is your router at home. And your router is actually something called a multi-layer switch. It does routing and switching. And so that central node is going to provide a forwarding function, and it's going to send it to wherever it needs to go, right? Maybe even in your house. So that is your router in your case. Then we can also organize bits into frames. So that's going to happen at the layer 2 level. So the data link layer is going to organize a stream of zeros and ones, right? Because that's what computers read, is zeros and ones. And so this is going to be structured into a unit called a frame, and that's at layer 2. And so each frame is going to contain a network layer packet and its payload. And then the data link layer is going to control information to that payload in the form of a header, right? And that's what we talked about earlier. Those headers are going to kind of give information. The fields here are going to be sources and destination of the hardware address. And that hardware address is that MAC address, right? So we have our destination and our source hardware MAC addresses. This also can provide us with error checking. So the last part of the frame usually has some sort of error checker. And so the protocols at most layers are going to have some sort of consistency check to verify that the data was actually transferred correctly. So the data link layer can only do like basic checking, but it can still do it. All right. Flow control. You don't really need flow control. Media access rules and logical topologies. So we have several different types of topologies here, and these are kind of like how we have them set up, like our connection set up on our network. So a bus topology is going to, everything is going to plug up into one like long wire basically. And here, let me get a picture for y'all. A bus and a ring. So bus topology. So this will be a bus topology. So we got this one long backbone cable and everything else connects to it, all right? And then we also have a ring-based topology. And we'll get more into these a little bit later, but I just want to show you what I'm talking about. And so each of them, all the computers will be connected in a ring around each other, basically a big loop. And then we have something called a star topology, which is what you're pretty much using at your house. And so this will be the central one, right? This is your router or something at home. All right. So that's logical bus and a ring. So this is a frame, an example of a frame. So it has the error checker, it has the payload, which is the data, and then it has the source address and the destination address. So your address and where it's going. All right, so layer 2 devices. We have the network adapter or network interface that's called a NIC. So a NIC is going to join the host and to any network media. So this is either maybe your Ethernet plug, right, or maybe your wireless card, and this is going to let it talk to stuff over the internet. All right, and then we have a bridge. So a bridge is going to take two network segments and bring them together. Bridges has multiple ports, and I'm probably, oh, here, get a picture of a bridge. I was about to look for you one. All right, so here's a segment. These are all on a switch or on a hub, and this bridge is going to allow this network over here to connect to this network over here. Without it, they couldn't have. And we have switches. So this is a type of bridge that has many ports, and a switch is going to help create links between large numbers of nodes. And then we have wireless access points, so we all know what those are. Pretty sure you connect to one every day. Uh, All right, so this is IEEE O2 standards. So there's been a lot of protocols, standards, and products that deal with the physical and data link layers for the OSI model. So there is these IEEE O2 standards are published by a standards committee, the IEEE, and it's a professional body that's going to oversee the development of electronic standards. So the IEEE is going to split the functions of the data link layer into two different types. So we have the media access layer, which is the MAC address, and then the logical control layer. And so in is it gonna talk about it more over here? I have to talk about it. Okay. So we have the 802.2, the logical link controller sublayer. So this is gonna provide us with a standard interface for our network layer, and it doesn't matter what type of protocol that the other that the MAC address layer is using. So in this case, the logical link sublayer is going to be used with other protocols such as Ethernet or Wi-Fi, and it's going to provide a standard interface, right? And then we have the 802.3, and that's going to be the media access control sublayer, and that's going to define how multiple network interfaces share a transmission medium. So like, how are they all going to connect to a bus or a ring? How do they address? How do they check frames and stuff like that? You don't need to know much about this unless you're going to get really far into networking one day. So then we have layer 3. And so layer 3 is probably what a lot of us are more familiar with. So layer 3 is responsible for moving the data around a network of networks. So it's the internet. So when the data link layer is going to be capable of forwarding our data by using hardware addresses that are in a single segment. So they are able to forward things to everybody that is on your router, right? But we need to get out of your house and go out into the world at large. So we're going to have to use routing for that. So so we're going to use the network layer is going to then transfer information between networks by examining the network address, right? The IP address, and route the packet through a whole bunch of other routers throughout the internet. And then as the packet moves router by router until it hits its target, and then it can say it's been delivered, right? Then we have a layer 3 switch. That's pretty much what you're using at home. So they have routers that are specifically for routing, but your thing at home is a switch too. It can connect everything in your house to each other and all that. So that's called a multi-layer switch. So a multi-layer switch does routing and switching. And then we have a basic firewall. You can have a software firewall, or you can have a physical one, but it's a router that can communicate and have a security function, and it's able to prevent any unwanted traffic from entering your local area network or exiting it. And then what do we got next? All right, so switching versus routing. All right, so we can have a WAN firewall. So that is a firewall. This WAN, that's meaning wide area network. So they're trying to protect themselves from the internet at large here. Then we have a LAN router, so that's what you're getting at home. And then you can have different sub networks. So maybe if we're working in a large company, we're gonna have a sub network for the finance department, one for the HR department, one for IT department, and then a backbone. A backbone is a high bandwidth segment that is able to be used between the router and the switches. And these are the switches. Here's the router. So it's going to be able to carry high amount of traffic, basically. All right, so layer 4, this is going to be the transport layer. So the first 3 layers of the OSI model are pretty much concerned with moving frames and stuff between nodes and networks. But at the transport layer, this is going to be the host to host. So the contents are going to be more significant for us. So we're going to have data like the HTTP data, which is stuff that's going to be on the internet. I mean, that's as port 80. So as it says, packages are going to be, we can identify these as port numbers. Can I be heard here? Because I got a pop-up saying I didn't have an internet connection for a second. Hello?
It froze temporarily.
Where did I end up? Where was I at?
It was very temporary.
It just paused for like a second and then went back on.
Okay. All right, so it identifies data via port numbers. So port 80 is going to be our HTTP traffic. Port 443 is going to be our secure HTTP packet. It's gonna when it sends the data, it's gonna be packaged as PDUs, which are called segments. So that's the pieces of data. That's what it calls them. And it merges. It can merge segments into from different applications over the network. And then it's able to send these out. So these are going to be multiplexed using the port numbers that are going to the same network link. And then the port numbers can reassemble the data for the appropriate application, right? And that's going to be deplexing. And then reliable delivery. So this also, the transport layer ensures that we have a reliable data delivery. So this means if it loses any packets or it damages any packets, it's supposed to go back and retrieve them. And then devices working at this transport layer can also work as load balancers. And so that way we don't overflow our system. All right. All right, so there can be unreliable delivery, and that's called connectionless. And then we have connection orientated, which is going to be connection delivery, in which we make sure that we get everything. Devices that are on the layer 4 level include multi-layer switches, which are your routers at home. And then we have security appliances, our firewalls, which are going to help to secure unwanted traffic from coming in the network, and the IDS, which is an intrusion detection system. And we can discern certain type of traffics and decide that we don't want that enter in our network. And this will alert you if one of those types of things get onto your network. All right, so the session and the presentation layers. So once we get up this high, like there's not so many protocols that we're dealing with here, but they have functions that are going to allow interfacing between the transport layer and the session layer. I mean, the software applications themselves. So most application protocols are going to require the exchange of multiple messages between the client and the server, the client being you and the server being whatever you're trying to connect to. And so this exchange of messages is a session. So when we get on Amazon.com and we log in, we've established a session here. So that's you're logged in, and that is your series of messages, right? So the session layer is going to represent dialogue control of this, right? We're going to manage the data function transfer, when we're going to end the session, when we're going to restart it. So sessions can work in 3 different modes. So we can have one way in which only one system is allowed to send messages and the other one only receives. We can have 2-way, which is also called a half duplex. This is when the host system is going to establish a system for taking turns on taking the messages and when they're going to take those turns. And then we have a two-way simultaneous, which is a duplex. And so that means either the host and the server can send messages at any time. And then we have layer 6. So that's our presentation layer. This is gonna transform the data required for the network, transform it from the format that was required for the network layer and transform it for the application itself, so we can see this, right? So for example, they're gonna use like character set conversions. So whatever the network had it transformed into before it got to you, the also, I'm freezing again, I guess. Am I back? I keep on getting pop-ups saying I went on.
You are back.
All right. So we stopped off. We heard ASCII, right? So the presentation layer is gonna transform it from just bits of data into ASCII, which is our human readable formats. And then the presentation layer also supports data compression and encryption. So that way we can make sure people don't know what we're talking about. And then we finally have the application layer. So that's layer 7. It doesn't encapsulate any other protocols. I mean, and well, nobody encapsulates it. So the application layer is going to provide an interface for software programs and the network host to establish communications through these other lower level protocols, right? And so different operating systems and file systems may use different naming conventions, different file formats. And so the application layer has to be able to get around that. And so it's important that we distinguish between the network application protocol and the software application. So we're going to have programs and shared programming libraries. And so we are going to have things like APIs, which are application programming interfaces. So this is going to allow us to have services like file transfers, email, web browsing, name resolution, WinSocks. Those are session layers. So making sure that you can have your session with whoever you're making your conversation with, and yeah, so APIs can be written for any layer of the stack. So in summary, we have the application layer. So what's on the application layer? Well, all three of these actually. So application protocols, this is going to be our web, that meaning HTTP, our emails, our downloads. This is all coming through well, the protocols used to establish these are on application presentation and session. And this is going to be done with multi-layer switches and stuff, which is what you have at home. Then we have our segments in the transport layer, our network, which has IP addresses, the basic firewalls, and there's done with the router. The data link layer, which had our frames and our MAC addresses, which was our physical address on that computer itself, or phone. And then the transceiver, which was establishing, the connection to the internet, basically. And yeah. So discussing the OSI model layers. You have a quick activity on Canvas. You should see it under lesson 1. So, all right, so we should have all finished activity 1-1, correct? Everybody's done with 1-1? I'm gonna take that as a yes. All right, so all right, so the next topic is the I need to get back on, huh? All right, share screen. Okay, so the next topic is the TCP/IP suite. This is another. It's similar to the OSI model, but it's only 4 layers, and they say they came up with this one because there's different. Not everything fits the placement on there. I believe that's what we're talking about here. Yep. So in this case, we have the link layer, we have the internet layer, the transport layer, and the application layer. So protocols are procedures or rules that are that are used by computers to communicate. So for communications to actually take place, they have to have a protocol in common. So there are several protocols a lot of times that are designed to work together. And in this case, it's going to be called a protocol suite. All right. So we have several protocol suites that are used for LAN and WAN communications. And most of them, the majority of them are TCP/IP suite. All right. So most of the network implications are going to depend on the use of that, and implementations are going to depend on the use of that. So we kind of map to the 4-layer model here. And so we got those ones that we just went over. And then so we can kind of see how this matches up to the OSI model, right? So link comes with the data link and the physical layer, and that's going to be the link or network interface layer. Then we have the network layer, which just becomes the internet layer. Transport layer stays transport layer, and then the top 3 layers are all together. And so all of these are going to work together, and that's why we have what's called a protocol suite. So we have DHCP, BootP, DNS, all of these working together, and we'll talk more in depth about all those as we go forward. All right, so we have our link network interface layer. So this is going to be the equivalent of that physical or data link and the data link layer. And this is going to define how we actually, the host, us, are going to connect to any network media. Media meaning wires and radio waves, right? So this layer includes, and I really want you guys to remember this, when we talk about media, anytime I mention media in security or in this, in networking, 9 times out of 10, maybe even 99 times out of 100, I'm talking about wires and radio waves, not media as in streaming media. It will say streaming media or something like that. So this layer is going to have the hardware and the software that's going to be involved in interchanging the frames between these hosts. So we can have LAN, which is going to be Ethernet or Wi-Fi, and we can have WAN, which is it could be ISDN. That's one of them. Another is DSL, but those are just involved in there. So in the internet layer, we have the internet layer, and this is going to have IP and ARP. So our IP is our internet protocol, the addresses and stuff. And then we have ARP. So that's address resolution protocol. This is going to kind of figure out where each MAC address lies on a in a table. So what do I want to say about ARP here? So it's going to kind of help us facilitate the packet. So ARP, maybe it's sometimes thought of like it's just working at the layer 2 model because we're dealing with MAC addresses. But layer 2 protocols don't need the Ethernet for the ARP to function. So we kind of want to think about ARP as a layer 2.3 protocol. because it kind of walks the line between layer 2 and in the OSI model. It would have been layer 2.3, like 2.5. Because it kind of straddles that line between just MAC addressing and IPs and stuff. All right, and then we have the transport layer, and so there's going to be TCP and UDP. So if anybody remembers what TCP and UDP are, this is going to be establishing our connections between different applications and that the source and the destination hosts are communicating with. So we're going to have things like we're gonna have two different methods to do this. And so we'll have connection orientated deliveries, which is gonna be TCP. And so connection orientated meaning they care whether you receive these packets, right? It's gonna have a checks, it's gonna go back and check to make sure that every last packet was delivered. UDP, if you guys recall, UDP is user datagram protocol, and it does not care if you receive what it's sending out. It is broadcasting. So Netflix doesn't care if you don't get it, right? If you've dropped packets once you started a movie, right? If it loses its connection, it's gonna stop. But if it's having problems getting a couple packets, it might skip or something like that. Well, Netflix has gotten really good about skips and stuff like that now on. But I'm sure a lot of you guys have remembered watching things online and they skip. That's because it doesn't care whether you get it or not in order to stream it to you, because it would be useless for it to come back and try to retrieve packets that have already passed, because TCP will go back and retrieve those packets, but it will skip over them for a certain amount of time and then go back and get it. All right, so we have packet switched versus circuit switched networks. So so TCP/IP was basically created like in the 60s and the 70s by ARPA. So I don't know if many of you have ever heard ARPANET. That it was the original internet. So ARPA is the Advanced Research Projects Agency, and it is I'm not sure if they exist anymore, but they would have been under the DoD if they do still exist, and they are. And if they do still exist, I mean, if they did exist, they'd be under DoD, and if they do exist, they're under DoD, which is the Department of Defense. And so the DoD wanted to build a network to connect several different military sites around. And so the prototype was called ARPANET. And so this was, they contracted out several universities to help them with it. The only one I can think of off the top of my head that I'm for sure was Stanford was one of them, which is kind of goes to show why so much of our internet infrastructure and major corporations come out of the San Francisco Bay Area, because that is where Stanford is located. The DoD, the Pentagon is the headquarters. We here in the Washington, D.C. area, 70% of all traffic that in the world comes through the D.C. area. A lot of that probably has to do with the fact that the Pentagon and Department of Defense are here, but also because AOL was one of the originators of commercial internet, and they were here too. But anyway, so for this ARPANET, they use something called a packet switching network, right? So prior to this, they communicated in a direct channel, which was known as a circuit. So a circuit is going to be a dedicated path established between two locations, such as a router or a modem. So the circuit could be permanently available, but in a circuit switched path, the routers are going to negotiate a link. And then once that link is established, then all the communications can be forwarded along the same path. And then at the end of the communication, then the connection is broken down and the path is available for somebody else to use. If this connection is ever broken, though, all the computers would stop communicating immediately, right? So that's why we had packet switched, because in packet switching, this allows the ability for one host to forward information to another using any available path. So we could bounce, we don't have to have a direct link. We can go boom, 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 boom. Or if it doesn't work out, then it reroutes the packets around any other available path. So if there's a damaged line, and that's one of the reasons why it's the military was involved here, because they're worried about damaged lines, right? They were worried about redundancy and stuff like that. So if there was a damaged line, it can reroute. So that is going to be packet switched rather than circuit switched. All right, so next up we have the Internet Society, the ISOC. The ISOC is an organization. The purpose is to encourage the development of and availability of the internet. And it provides resources to the Internet Architecture Board. And so the Internet Architecture Board is a committee of people from the ISOC, and they are responsible for setting internet standards. Internet standards such as Internet IETF, which is the Internet Engineering Task Force, which is going to focus on internet problems and new standards for the internet. Then we have the Internet Assigned Numbers Authority, IANA, and they are who allocates out IP addresses, and they maintain top-level domain space such as .com, .org, .gov, .edu, and the function, they allocate all these. They also allocate these addresses regionally, and then local ISPs such as Comcast or whoever are going to divvy out them further. When they first started out, because basically we are out of internet IP addresses, IP4 addresses. There's only something like 4 billion. And so when this first came out, they were just tossing them out to whoever. Universities got like huge swaths of these, and now these are very expensive. So they had to do some workarounds to make sure that we can still connect to the internet because there's not that many IP addresses. So what happens is in your house, you have a private IP inside your house, and your router is actually talking for you with the main IP. So anyway, there are different regional registries that hand out these ISPs as well. So they have Asia and Pacific, and that is APNIC. Then they have North America and South Africa. And they're going to be ARIN. And then we have Latin America, which is LACNIC, and I think RIPE is like North Africa, Europe, and Middle East. And then we have requests for comments. So and that's RFCs. So since TCP IP standards are going to be developed by consensus of these people, there's a process for them to adopt new standards. And so that's called the request for comments. And so the standards are going to be published in these requests for comments, and they're going to describe new things. And so if there are any new requests for comments, they'll be published, and you should, they say you're supposed to like verify that you have the most recent request for comments on a particular topic or subject, because some of these are informational and others might be experimental. I don't know. I haven't really dealt with them that much. Just know what they are. And that's all you need to know for if you decide to take the Network Plus test. All right, so the final activity of this particular lesson is going to be discussing the TCP IP suite. So please go to activity 1-2, which is probably directly beneath activity 1-1. Any questions?